Thank you for clicking on the link and coming here. I'm going to speak about applications of random algebraic constructions to hardness approximation. This is joint work with Boris, Bukh and Bhargav, Narayanan. In order to motivate the problem that we considered in this paper, let me start with the standard K-set cover problem. It's a popular NP-hard problem where we are given a collection of sets and we want to determine if there are K sets in our collection whose union is the entire universe. This is a known hard problem. It's known hard in fine-grained complexity, parameterized complexity, the standard NP world. It's hard in many different regimes. And we can consider a colored variant of this problem, which also appears a lot in literature, which is the colored K-set cover problem, where we are given K collections of sets, and we would like to determine one set in each collection whose union is the universe. So we are asking for picking one set in each collection such that it maximizes the coverage. And in this case, whose union is the entire universe. And we ask, is the colored version and uncolored version computationally related? Or in other words, are they equivalent? And indeed, for this specific set cover problem, one can show that the colored and uncolored versions are computationally equivalent up to constant factors depending on K. So for instance, you can go from the uncolored version to the colored version by using the standard color coding technique. And from the colored version, we can go back to the uncolored version by adding some dummy universe elements, which forces you to pick one set from each color class. So this is for the K set cover problem. But there's a related K set intersection problem where we are asking, given a collection of sets, find K sets whose intersection size is maximized. So we say an element of the universe is in the intersection if it's there in each of those sets. This is the standard K set intersection problem, and it's a notoriously hard problem. And the colored variant is where you're given K collections of sets, and we would like to pick one set from each collection whose intersection size is maximized. And here it's an open problem whether the colored and uncolored versions are related. And in fact, we can ask a broader question with respect to any optimization problem, like say the clique or clustering, any optimization problem. We can formulate a colored version and an uncolored version and ask if they're computationally related. And in general, it happens that it is easier for one to prove hardness results for the colored version. And then we would like the hardness result to hold also for the uncolored version. And we want to know if this is possible by just a reduction from the colored version to the uncolored version. Now note that we can always go from the uncolored version to the colored version by using the standard color coding technique. But can we reverse color coding is the big question. Can we do a reduction from the colored version to the uncolored version? And in this talk, I'm going to focus on the set intersection problem and show that indeed, yes, we can go from the colored version to the uncolored version, which at a high level or an abstract level says that we can reverse color coding for this problem. So let's again focus down on the set intersection problem. Here we are given a collection of sets and we want to find K sets in our collection whose intersection is maximized. And I will do a quick literature survey as to what is known for this problem. K set intersection in the NP world is notoriously hard to prove even hardness result. And in fact, it is still an open problem to prove that it is NP hard to rule out, say, a PTAS, a polynomial time approximation scheme. So we do not even know how to prove hardness to a factor of 1.0001, assuming P not equal to NP. But of course, using a much stronger assumption, say called weak ETH, which says that 3CNF cannot be solved in time 2 to the n to the epsilon for some positive epsilon, we can rule out polynomial factor approximation algorithms running in polynomial time. But even to prove this result, which is on a much stronger assumption, we need a highly non-trivial construction of quasi-random PCPs. So even to prove something weaker, we need some extremely heavy tools. What about in the FPT setting, the parameterized complexity setting? Bing-Kai-Lin in a breakthrough work showed that no algorithm running in FPT time, which is T of K poly n time for some computable function T, can even approximate the K set intersection problem to f of K factor for any computable function f. So this is a very strong result. And it came out of nowhere, essentially. And in fact, in the same work, he showed that assuming the stronger exponential time hypothesis, there is no f of k factor approximation algorithm running in time n to the omega square root k. Notice that one can solve the k-set intersection problem exactly in time n to the k by just going over all k tuples n to the k plus 1. And this says that you cannot do significantly better, although it's not really tight, because ideally one would want to show that assuming ETH, no algorithm running in time n to the omega k can approximate k-set intersection to any f of k factor. But there is some gap here. But now let's look at the colored version. What can we say about the colored version? Well, in the colored version, we are given k collections, and we would like to find one set in each collection whose intersection size is maximized. And in the NP world, this is some variant of the standard label cover problem, which comes from the PCP theorem. And we can prove insanely strong hardness approximation results. And in the FPT world, we can rule out essentially everything, that in assuming T of k poly n time, there is no f of k approximation algorithm, which is called the max cover problem in the work with Bandit Lekanukit and Pasin Manurangsi. And in assuming ETH, we can rule out the tight, that the best you can hope for, that is no algorithm running in n to the omega k time can solve, can approximate it to f of k factor. When I say n to the omega k, I say that there is some small constant epsilon k. No algorithm running in n to the epsilon k time can approximate it to f of k factor for any computable function f. And in fact, assuming the strong exponential time hypothesis, we can show that no algorithm running in n to the k minus epsilon time for any epsilon, positive epsilon, can approximate it to f of k factor. And in fact, in the color version, to just go get exact hardness, assuming these assumptions, is fairly straightforward. And the non-trivial part comes in generating the gap. But so one can see that for the colored version, we can essentially say everything there is to say, and at the high level. But for the uncolored version, we are far from telling the right things. And the main result in this work is to show that the k-set intersection problem, the colored and the uncolored versions, are computationally equivalent up to constant factors depending only on k. In fact, we can extend our result to say that if there is some C approximation algorithm, if there's some algorithm that approximates the k-set intersection problem to some C factor, then such an algorithm can be used to approximate the colored version to some C over h of k factor for some fixed function h depending on k. So by setting C to be a much larger function depending only on k, we can rule out any f of k approximation algorithm. So in other words, we now have a tight understanding for set intersection problem. We have that assuming W1 not equal to FPT, we can rule out any f of k factor approximation in FPT time. We can rule out the same any f of k factor running in n to the little o of k time. We can rule out any f of k factor running in n to the k minus epsilon time. So we have now a tight understanding from our work of the k-set intersection problem. And the main technical object that we built in order to prove the equivalence between the uncolored and colored version are these things called panchromatic graphs. Panchromatic graphs are bipartite graphs with two sides. And on the left side, you have the U1 to UK. So you have the vertices being partitioned into k color classes. And on the right side, you have W. And for the rest of this talk, I will consider the size of each UI to be the same and equal to n. And what would we want from these bipartite graphs is we want that every k tuple that you take, one from each color class, has exactly t common neighbors in W. So as long as we pick U1 in U1, U2 in U2, UK in UK, regardless of which particular one I pick, any k tuple that is panchromatic in one from each color class has going to have t common neighbors in W. Whereas if we pick any k vertices in U which skip a color class, or in other words, equivalently repeat a color class, then we'll have only t minus 1 common neighbors in W. Okay. And then the question is, does this graph exist? Of course, if we let W to be very large, say n to the k, then maybe it exists. But does it exist for small w? Where small here means, say, when it's the size of U, let's say, or even smaller. Now, these graphs were studied previously in a work for k equals to 2 by myself and Pasin Manurangsi. And here we looked at the constructions when there are two color classes instead of K. And we wanted the same thing. We wanted that every pair across, one in U1 and the other in U2, should have exactly T common neighbors. And every pair of vertices within the same color class, both in U1 or both in U2, should have at most T minus 1 common neighbors. And we asked the question, does it exist for small w? And we indeed showed that it does, with a small caveat. We showed that when w is polylog n, so it's polylog n in the polylog the size of u, then we can construct it with the caveat that it's not true for every pair u1 and u2, but it's true for many pairs. And that sufficed for the applications we had there in mind, which was proving fine-grained complexity of the closest pair problem. But here we ask it for a general version where you have k tuple instead of 2. So this question still remained at large, and it was indeed proposed in the previous work. If we can find these objects which have k color classes and still have this property, but for many instead of every. And the main result of our work is that they do exist. In fact, a much stronger object exists. And the result we show is that for many of them, where many, you can think of it as some fraction depending only on k, independent of n. So 1 over exponential in k or something like that. So for many of them, we have exactly T common neighbors, whereas as long as it's a panchromatic k tuple. But if you take any k vertices which repeat a color class, then they have at most T over f of k common neighbors, where f is any computable function of our choice. So we can really create a gap between the two things. And we can achieve all this when the size of W is exactly the size of U. Now, one can ask, do random graphs from the Erdős-Rendley model satisfy this? And the answer is no, they don't. So there is something really non-trivial we'll have to do, because random graphs don't obtain this property. And why such an object is interesting, we are going to see that how it's going to be used. At least I'm going to give an outline of how such a panchromatic graph is going to be used to reduce the colored version to the uncolored version. Notice that the colored version can itself be formulated as a bipartite graph, where we have the sets on one side and the universe on the other side. And the sets themselves are partitioned based on the k collections we are given. And we would like, in the yes case, one collection, one set from each collection, such that it covers the entire universe. And in the no case, so the notion here is the total neighborhood, right? And in the no case, if we pick any k sets, as long the only guarantee we have is that if the k sets are from one from each collection, then they don't cover the entire universe. But we don't have any guarantee when you pick, say, sets from the same collection, all k sets or like many of the k sets from same collection. So we want to reduce this colored version to the uncolored version. So we incentivize any algorithm to pick sets from the same collection, or rather we penalize when an algorithm picks sets from the same collection. So this is described as the panchromatic graph composition technique, where we have the input instance, the bipartite graph here, and we have on the other side the panchromatic graph. So we overlap the set U, the U vertices, onto the C, because both of them had these k collections, and we pair them up 1 to 1. So we have this tripartite graph. And the idea then is we sort of take the product of the two green sets. And so we put an edge from a set to a pair AW, where A is a universe element and W is a vertex from the panchromatic graph. If A is covered by the set, that is A is contained in the set, and A and W on the set had an edge in the panchromatic graph. Notice that if the k sets were coming from one set from each collection, then we will have that the universe is entirely covered. And at the same time, because it's one from each collection, we have a lot of common neighbors generated because of the panchromatic graph. Whereas in the no case, if we pick either that the k sets are from one from each collection, but they don't cover the entire universe, then the gap that is generated comes from the input. But on the other hand, if we pick k sets from where we repeat a color class, then we know that even if it covers the entire universe, we know that not a lot of common neighbors exist from the panchromatic graph. So we create a gap from there. So either the gadget helps us to force that we pick from the colored instance, from panchromatic instance, and once you pick from the panchromatic instance, the hardness from the colored instance follows. And how do we construct these graphs? Since random graphs don't satisfy it, then we look at polynomials, and they have always been helpful for us, and we construct them using polynomials. So the idea is to pick first k random polynomials, each of them being k variate over fq, of degree at most some capital D, where we pick D, some suitable D later. And our UI, which is the, the vertices on the left side, the k color classes, the UI is going to be defined as, first we pick n random polynomials, which are k variate again, but of degree D, little d, which is much smaller than the uppercase D. So you have, say, P1, P2, P up to Pn, and you're going to associate to UI the polynomial, like the vertices, every vertex in UI is going to be the polynomial Pj plus Wi, where j runs over 1 to n, and the Wi is fixed for UI. So you're going to, in some sense, take n random polynomials and shift them uniquely by Wi for the ith set of vertices, collection of vertices. And our W is just going to be the evaluation, where we are going to evaluate all these polynomials. So it's fq to the k. And we put an edge from a vertex in UI, say say it's denoted by P plus Wi, where P is this degree little d polynomial. We put an edge from P plus Wi to alpha, where alpha is a place where we evaluate this polynomial, if P plus Wi evaluates to 0 on that location alpha. Notice that Wi plus P is uniform over the space. Now, our technical result then is that we prove some probabilistic analog of Bézout's theorem, where we say that if we pick k independently k variate random polynomials of degree little d, then the number of common roots z, there is a strong threshold phenomena for the number of common roots that they have over fq to the k, which is that if the probability that z is exactly d to the k is quite noticeable. In fact, it only depends on the degree and k, and here the degree depends on k, so it's only dependent on some k. Whereas if you want even one more, the probability that the number of common roots is d to the k plus 1 is vanishingly small. It depends on the field size, which is a function of n, so it goes down dramatically. So we have this very strong technical result. So let's do the analysis very quickly. Suppose we pick one polynomial from each UI. So it's of the form Wi plus Pi, say. Then the common neighborhood on the other side is just the number of common solutions to these k random polynomials. And it's distributed uniformly, more or less. And we can use the previous result we had and claim that the number of common solutions that they will have more than d to the k is vanishingly small. But the number of common solutions that they will have that is exactly d to the k is some function depending on d and k, which is good for us because d is a function of k. And these are degree d, capital D polynomials. Whereas in the no case, if we skip the color class, say we skip the first color class and we pick k polynomials, then notice that there is a color class where we repeat a polynomial. So we have two polynomials there, and their difference is going to be a little degree d polynomial. So in that, you're going to distribute over little degree d, and that has vanishingly small probability, which is the common neighbors is going to be much smaller there. So in conclusion, we have these amazing graphs exist. And so we have these set of results. And in fact, in our work, we also give a new proof to Bin-Kai-Lin's thing by constructing threshold graphs, which he calls, which are these really non-trivial objects where you have a balanced bipartite graph such that if you pick any k neighbors in V, then they have at least n to the omega 1 over k neighbors in A. But if you pick any k plus 1 vertices in V, then they have a very small number of common neighbors in A. And we show these exist as well. And to summarize, panchromatic graphs exist, and they are used for tight running time lower bounds for approximating parameterized set intersection problem. Now, there are two main open questions stemming from our work. One is, can we explicitly find these panchromatic graphs? Because all we do is give a distribution, but it would be nice to have an explicit construction. And are there more applications to these graphs? Because it feels like they should be applicable in different scenarios. Thank you.